Hello everyone, I'm Syun'ichi from Princeton Plasma Physics Laboratory. So I'm going to talk about radio frequency wave simulation for the fusion plasmas. So just for the introduction, what we are doing is wave simulation on mostly fusion plasmas, but also other devices. So equation we are solving is simply put this kind of equation, second order Maxwell equation for the electric field. But what is complicated for fusion plasma or in plasma general is this epsilon, which is the electric property. It's not a it's not a constant. Instead, it's not even scalar. It's usually 3 by 3 full matrix tensor, and that is a difficulty. Although having that said, with the MFEM, we can solve a pretty large problem. So the right one, the wave simulation, which we did for the NSTX spherical tokamak, which we have in the Princeton Plasma Physics Laboratory. And you can see that there's many wave oscillations excited from the antenna and propagate toward the plasma. And roughly, in this case, we use order 4, and the degree of freedom is 50 to 100 million degree of freedom. Other simulation here, this is the wave excited by here. It's a simulation of the a space plasma. This is a planet here, and the sun. Basically, what happens is sun, solar wind comes here and excites the wave, and the wave propagate is excited. The other one here is a 3D simulation of the ECL thruster, which people use for the propulsion in the space. Okay, so I said we can do a lot, very big problem right now, pretty happy. But one issue is this dielectric property, which is not yet fully, which is a place which we would like to improve. So before going that, let me show you 2 slides about the tools we're using. So we are using MFEM, but we also in addition to MFEM, we put together multiple libraries here and combine them and develop some integrated multiphysics platform, which we call PETRA-M. So essentially what we did is we took a variety of different open source libraries from geometry, meshing, and MFEM, other things, linear solvers, and we developed, when necessary, wrapper for this library to use them in the Python. And we built a physics layer on the top of this C++ or Fortran written library to do the simulations. And this scheme allows us to do 2 things. One, we can develop the physics model pretty quickly through graphical user interface, and also provide a custom graphical interface for setting the physics. And that is important because even say we say plasma, the dielectric response of the plasma can be, there's a variety of response model with different complexity. Here on the top, this is so-called cold plasma response. This is something which 95% of people uses when people does the FEM simulation of the waves. And here, so this S and D and P is a function of plasma density, magnetic field, and wave frequency. So when we do the simulation on the physics side, we want to use these physics parameters instead of thinking about what is S, what is D. So that's why the user interface is important. Now, I said 95%, so remaining 4% of 5%, remaining 4% uses something like this, which consider the plasma as Maxwellian plasma. So as you can see, it's already 3 by 3, 9 element fully filled matrix with a bunch of difficult and complicated features, functions inside. And what is the problem here? It comes here. That is, these functions, this is a modified Bessel function, and this AN, it comes from so-called plasma dispersion function, depending on the wave number. Wave number because we are dealing with magnetized plasma, wave number is not a single number. There is two wavelengths in the direction parallel and direction perpendicular. So we call it k-pap and k-parallel. So now I said 4%. So what many people does, because it is depend on k, you don't know k until you solve it. So then you cannot use this form. So what people does is assume k, pretend I know k, and that's what many people does. Many people does not because they are wrong, because in many cases it's really valid. But certain situation, we really don't know what kind of wave number we have. Then we need to really seriously treat this form diligently. So now, why this is important? Because our plasma is hot. Well, we want to do fusion, so it need to be hot. And when it becomes hot, then in the plasma, a charged particle can move freely along, especially along the magnetic field line. So it doesn't collide. So if you have the electric field, wave field here, and then charged particle moves, zero motion, then what happens is, for example, this ion pick electric field here, then freely moves along the magnetic field line, and then it produces a dielectric current everywhere along the magnetic field line. It spread also because of the motion. The information picked up here is spread perpendicular to the magnetic field line. So in the textbook, this is almost so. J equals sigma conductivity times E. What is hidden is there's argument K, which is a problem. And as you can imagine, if you fully transform this, it becomes this way and becomes convolution kernel. That is an issue because for the finite element, convolution is not so easy to handle. Okay, 3 years ago at this meeting, at workshop, we encountered this, I can encounter this slide, which Tobias solved the fractional Laplacian, fractional diffusion equation. And where basically Laplacian is not Laplacian, but there's alpha, which is not on 2. And that I found it interesting because if you look at Wikipedia, I didn't know about fractional calculus at the moment at all, but I found that this has a connection with non-locality. So I thought about how to incorporate this idea to a wave simulation, and I did. In fact, year after I present something early result in this meeting, and what I'm going to show is follow up of that. And there's a lot of progress because at that time, even though, going up, here I have 3 by 3, 9 free parameters. I only dealt with 1 parameter. Now, today I'm going to talk about dealing with every parameters. So, okay, so how do we do this non-local response model? So let's skip this slide because it's not necessary. So what we found in the short run, what we needed to do is if we have conductivity Ohm's law like this, then what is need to do is this sigma. Let's say I said K has a 2K wave number perpendicular to parallel, but let's say assume this is a function of K-pop, okay? Then we expand this using rational approximation like this. Then take the each term, and then it has like this, right? Then we just need to bring this form, denominator, on the other side, and then replace this K-pop to the gradient. And then it becomes like this kind of diffusion equation for the J1. Of course, we need to do the same thing for all of these terms. So therefore, it becomes entirely this J becomes summation of J1, J2, J3, J4, depending on how many terms you use for the rational approximation. But you can do it. So finally, this is a little bit different from the fractional diffusion equation because we want to solve the Maxwell equation. So we don't stop here. Instead, if we take the E, we need to bring this J back to the Maxwell equation like this. So end result, final equation is a Maxwell equation and the diffusion equation, bunch of diffusion equation coupled together. And this D and C in this diffusion equation comes from rational approximation. So if we do it, there's several advantages. First, there's no, this now, because this is usual diffusion operator, we can use it, MFEM's operator, directly without thinking too much about non-locality and so on. There's no degree of global degree of freedom coupling, and because we don't do the convolution. Now, how does it work? Before going to show the result, one more thing. Now, there's one thing which we found later is this one. So in the plasma, our plasma has a spatial dependence. In other words, density and magnetic field change in the space. So if we write that equation like this, then this is not symmetric. So if you are not symmetric, it's not self-adjoint. So therefore, even the plasma is not supposed to absorb any power, emit any power, you got artificial, introduce such a thing. So what we did is symmetrize this one to this way so that self-adjointness is guaranteed if there is no absorption supposed to be in the plasma. Okay, so let's skip this one. This one just showing how the rational approximation works and showing that 5 to 7 terms is good enough to expand. And like I said, there is a K depending on perpendicular direction and parallel direction. And this one shows, and in even parallel direction, we can essentially do the same approach because what happens is all this, the term becomes a function of K parallel squared. So we can do the same rational approximation and then K parallel bring out to the left-hand side, and it becomes a diffusion operator with respect to the parallel direction, with respect to the magnetic. Okay, so let's move on to some example. So this is 1D simulation. So what we are doing, what I'm doing here is injection of electromagnetic wave 80 gigahertz in the particular case in the 1D simulation geometry from the right to the center. And the plasma is here. Okay, and then I put the artificial damping so that to clean up solution. So this is on the right, this is the dispersion relationship as a function of x. What I'm showing is wave number, perpendicular direction. So inverse of the wavelengths. So in this specific case, as wave enters the plasma, you can see there's 2 wavelengths happens. And so because there's short wavelengths and longer wavelengths, both are still electromagnetic waves. And then at some point, there's no solution of the dispersion curve. So solution here, it looks like this. This part is a vacuum. It's a clean, nice sinusoidal wave. As it starts, then it becomes big oscillation, and then wave penetrate up to only this point, which is this one. And then here you can see there's a wavelength because you can see the wavelength is very short because at some point it's called resonance. Wave number becomes super large. Now, if you introduce the non-local effect, then it becomes like this. So here, previously, there's this curve chopped out, but then there's other wave branch appears due to the thermal effect. And starting from that, there's waves propagate. So solution looks like this. You see that previously there's a short wavelength wave spike here, and there's nothing. But then waves start propagate to the center. And interestingly, if you expand this part, then wave front is actually moving right direction because this wave is so-called backward wave. Okay, so now, okay, let's move on to the 2D simulations. So like I said, we can do all terms. So that is 1D simulation. Now, in order to do 2D simulation, there's a and 3D simulation, there's 9 terms. We need to write it in vectorized form like this. And by doing this, we can basically do the same thing, same trick for 2D and 3D, although we haven't yet tried 2D, 3D. So again, this is a different simulation in 2D tokamak. It's a cross section of the donut plasma, and in this case, we didn't introduce the non-local effect. So wave is launched from here, propagate this way. There's a little bit of absorption here, so therefore wave the amplitude goes down. If I introduce non-local effect, solution becomes like this. You see, wave goes here, then all of a sudden, very different waves, with new waves with very different shorter wavelengths appears. And in this particular case, among 3 by 3 elements, what is important is this 2 by 2 block and this block. 2 by 2 block is important for electron ion behavior, and this block is important to capture the thermal response of electrons. So we introduced all of those terms, and we did this simulation. So this is so-called ion cyclotron waves. Now, this is different waves for each electron called lower hybrid waves, which only this term, electrons response, thermal response in the parallel to the magnetic field is important. And in this case, again, these are 2D simulation. Wave is launched from here and propagate this. And with different temperature, 3, 4, 5, 7, and 10 Kev, and you can see that as temperature goes up, plasma start to absorb more power quickly, so wave penetration becomes smaller. Finally, this is the same as the 1D electron simulation, but in the 2D. In this case, what is important is this 4 corner for the electron response. And again, in the same scheme, you can do the hot plasma, introduce a non-local effect, and therefore, wave is injected from the right, and the plasma is in this circular shape. And at the middle of close to the edge, but after plasma start, there is a short wavelength wave oscillation start, and wave front moves toward the right, which means this is a backward wave. Okay, let me summarize my talk. So we have been investigating a new formulation to introduce non-local response based on the rational approximation and derived differential operators. And this way, we avoid convolution integral, and we avoid convolution integral, and still we can capture the physics just using the second order standard diffusion operators. And we extended this to the full 3 by 3 order terms, and it looks like valid. And we tried different wave simulations for the different frequency and characters. And all of these ICRF, lower hybrid, and electron Bernstein, these are different wave branches which appears only, which non-local effect matters, and simulation results looks reasonable. Okay, this is the last slide. So everything looks good, but still there's a remaining major issues. One thing is, well, so we have the Maxwell equation, and we needed to extend to add a diffusion equation. And number of diffusion equation depend on the rational approximation, which can be large, typically 5, 6. So which means, and we are solving the entire linear system at once using a direct solver, which means you have a 10 times more degree of freedom. And because we need to use a direct solver because it is frequency domain, so therefore, Maxwell equation, this component is indefinite. Now, since these terms the remaining diagonal terms is regular diffusion operator. So there may be a good way to make it solve iteratively. That is one thing we need to address before extending this to 3D. The other thing, this is two, is we are right now relying on the rational approximation of univariate functions. So, however, as I said, there is K has two K perpendicular, K parallel with respect to the magnetic field. So, and we rely on the fact that this function is a product of separately, one function depends on K parallel, one function depends on K perpendicular. Well, it's not always the case. If, for example, plasma becomes very hot, then you need to introduce relativistic electrons and so on. Then this decomposition also, it doesn't always work. Then we need to think about how to do it. So hopefully someday I will come back and report the next progress. Thank you so much.
Hi, excellent talk. Looking at that operator at the top there, I'm just wondering, can you do some kind of like Schur complement situation to eliminate the J hot? Like if you didn't actually need to solve directly, or does that just make the system much harder?
Yeah, we tried that one, and it is very difficult because this one is when you do the Schur complement, you need the inverse of this, which we don't have it for the.
I was thinking more of like eliminating the Laplacian terms. So you'd be inverting so if it was A, B, B transpose D.
Yeah.
The D inverse term.
D inverse, yes. So
Okay.
if you diagonalize the inverse, it is still not accurate enough in that space. Yeah. And yeah, we don't have yet solution. We tried several things. And thank you.
Yeah. Just another question. Seems you can do some wave particle interaction simulation instead of doing this wave only, right? Will it be something you'll be interested?
In particle?
Yeah. You resolve plasma using particles and then shooting the waves.
Yeah.
And it will be very relevant to the early talk.
Yes, that's a very good question because, in fact, we thought about, or in the past, some people did use a particle to compute J instead of solving the diffusion equation. And that's doable. And still, issue is you need to couple it. Then once you couple it, then iteration does not really work well. And that is a kind of issue. But still, having that said, I was thinking about going back to a particular approach some point, because when you, for example, as I said, relativistic, it becomes this approach difficult. Then maybe sometimes particular approach may make sense in that regard. Yes.
Yeah, we have new particle modules, so you can.
Yeah.
Any question? Any more question?
What? I saw you raised.
Thank you. I was just curious about the backwards propagating waves. And in that case, it's the phase velocity that's pointed backwards, but the pointing vector is still in the forward direction, correct?
Yeah.
Thank you.
Exactly. Yeah.
Well, let me ask one more. So why do you use fractional Laplacian to resolve a non-local effect? There are other options, right? Or you can do some non-local closure. It's not working?
Wait, that's a difficult question. Well, short answer, if I constrain myself to use a differential operator, this is the only thing it came up to my mind. And other than that, convolution kernel, or the other option is, in fact, instead of doing this, right? If let's say this D1 is K pub is very, very small, then you can assume that you can expand this one. Then you don't do a different approach. But then if you do it, the validity of this approach is limited when the wave K-pub is small, which means wavelength is large. So we took this because we believe this is more general. Yes.
So there are some examples in laser generated plasmas.
Yeah.
And just something to think about. There is already, as Chi mentioned, closures in the K-space for non-local transport for laser-driven plasmas. So it would be similar to your formulas. I don't think it's the same one. So maybe just to compare to. I mean, Vladimir Tikhonchuk did something like this.
I'll come to you to get more information. Thank you. Yes.